and telling you, for example, that we're idiots to worry about Ebola that killed 2 Americans when more people slept with Kim Kardashian that year. Okay. So for example, and that was effectively the number they said, that more people slept with Kim Kardashian in 2014 or were worried about Ebola than died of Ebola, for example, right? So now, and then sometimes you see numbers like these, and this is the kind of thing that if you read something called the New York Times, and you still read that nonsense, this kind of stuff you read in it, which is factually right, but bogus, okay? Well, and the kind of thing that teach in psychology department, that so many Americans die from eating too many hamburgers, smoking too much alcohol. Now let's think about it in terms of tails. If I tell you, or let's say Steven Pinker gave the number that 3,000 Americans die in their bathtub every year. Okay, 3,000 people, whereas 2 have died of Ebola. Now let's play a thought experiment. If you read in the papers, if you go, to Mars and come back, and then read on, on Google News that 2 billion people have died, what's more likely to have killed them? Diabetes, obesity, falling in their bathtub, sleeping with Kim Kardashian, or Ebola? Ebola. Okay, there we go. So you cannot compare, rule number 1, thou shalt not compare a multiplicative, fat-tailed process in extremistan in the sub-exponential class to a thin-tailed process that has what we call Chernoff bounds, okay? And that is totally from mediocre stat. Simply because of the catastrophe principle, okay? And then we know, for example, that it's very cheap to protect yourself from Ebola. You see? The probability that people dying from smoking, okay, is multiplied by 10 next year is 1 to the 10 minus 30. The probability that the rate of people who died from Ebola triples is vastly higher, you see? So you cannot compare processes. Thin tail to fat tails are not comparable. So this is not empiricism, this is called naive empiricism. It's actually worse, okay? So you cannot compare 2 processes like these by saying we worry too much about Ebola. In fact, we worry too much about diabetes and too little about Ebola. So that's one error of reasoning that comes from not understanding fat tails. Now, let me show you the law of large numbers. Everything you learn in statistics is based on a well-functioning of a law of large numbers, no? All right, so in other words, it tells you that as you add observation, the mean that you observe would be very stable, no? And the rate is square root of 2, or square root of n, number of observations. You agree? All right. This is what you have on the left. Now, on the right, for a fat-tailed process, the mean exists, but it takes much longer to observe it. Much longer. You need many more observations, okay? I'm not going to go very far and cite the most commonly known statistical phenomenon. It's called Pareto's 80-20, on which later, technically, but now let's mention it. You've heard the Pareto 80-20, okay? 20% of Italian owned 80% of land, 80% of Italian owned 20% of remaining land, okay? 20% of students, you get the idea, all right? Okay? 80% of 20% of the activity that happened, after lecture. So you get the idea, all right? So that's the Pareto 80-20. So let me ask you, for some reason people in textbooks take 30 observations for the Gaussian to say how much you shrank the mean, okay? So I have n of 30, my sample. Your variance drops. How much do I need for Pareto 80-20 to bring down my variance by the same amount? Twice as much? 3 times? Someone help me? Sorry? How much? Twice? Okay, let's keep going. He said twice. You need twice. In other words, you need twice as much data to bring down your mean, to have certainty about stability of the mean, to shrink your mean. Let's continue.
I get 100.
How much?
100.
Keep going.
1,000.
Keep going.
10,000.
Who said what?
10,000.
Let's keep going. Who's the highest so far? This is the table here. If the mean exists, this is forget about it. The Pareto 80-20, 10 to the 11. 10 to the 11. In other words, it's a lot of data to have the same error with the Pareto 80-20. Okay? So, and this is trivial to compute, but for some reason people don't compute it. So you cannot make claims on sample mean, on the stability of the sample mean on the basis of data with a fat tail distribution. There are other ways to do so, but not from observation sample mean. Okay? So, now let me do some epistemology, some philosophy, because I know that this is a big place for it. And the Wittgensteins and Schmittgens, a lot of things here, and Russell. And then we go back to a little more destabilization of people who have studied statistics and economics, okay? So let's do some epistemology here, right? And I'm proud of it because it's the first paper I ever wrote. It took 5 years to write it. It's longer than writing a book. And let's say I observe a degenerate distribution, okay? Now there's no randomness. All observations come at 2, okay? Can I rule out that the distribution is random? I cannot logically rule out. We've known that from people in the UK claim Hume, but we've known that from Sextus Empiricus, okay? Via like another 75 people who asserted that, okay? That's a black swan problem, okay? You cannot rule out that you cannot say there are no black swans. Likewise, if I see a distribution that has no randomness, I cannot say it is not random. But let's say now I add one observation and I notice that effectively it is random because it's not all degenerate at 2. It has another observation. Can I rule out degeneracy? Yes, I can say it is not non-random. You agree? Like I've seen a black swan, I say the statement that there are no black swan is wrong.